Imagine for a moment that everything we thought we knew about the universe, its grand story from the Big Bang until today, might have a crucial chapter missing. Scientists, the people who build their careers on measurement and certainty, are now facing a profound mystery. It's a disagreement so deep it calls into question the very foundations of our cosmic understanding. We have looked out into the vast darkness, measured the cosmos with incredible precision, and found something that simply should not be there. A number that refuses to add up. This isn't a small error or a minor miscalculation, it's a fundamental conflict at the heart of modern cosmology. It whispers that the universe might be stranger and more complex than we ever dared to imagine. The story begins with a simple, yet monumental discovery. The universe is not static. It is not a fixed and eternal stage upon which stars and galaxies play out their lives. Instead, the entire fabric of space-time is expanding, carrying galaxies along with it like raisins baked into an ever-rising loaf of bread. This was the revelation of Edwin Hubble in the 1920s, a discovery that rewrote our place in the cosmos. Ever since, astronomers have dedicated themselves to a singular, vital task, measuring the speed of this expansion. This rate, known as the Hubble Constant, is one of the most important numbers in all of science. It tells us the age of the universe, its scale, and helps us to understand its ultimate destiny. For decades, getting a precise value for this cosmic speed limit was a messy business. Early measurements were fraught with uncertainty, like trying to clock a sprinter with a sundial. But technology marches on. Our telescopes became more powerful, our methods more sophisticated, and our understanding of the cosmos more refined. We developed not one, but two exquisitely precise ways to measure the expansion of the universe. Each method is a marvel of scientific ingenuity, built on decades of work by thousands of brilliant minds. They are the gold standard of cosmic measurement, designed to give us the final, definitive answer to one of the biggest questions of all: just how fast is our universe growing? The expectation was simple and beautiful. These two independent, high-precision methods should have given us the same number. They should have pointed to a single, unambiguous truth about the nature of our reality. Instead, they gave us a crisis. They delivered two different numbers. Both measurements are incredibly precise with tiny error bars, yet they stand in stark, undeniable conflict with each other. It's as if two perfectly calibrated stopwatches, timed by the world's best experts, gave two different results for the same race. The universe, it seems, has a secret it's not yet ready to share, and this discrepancy is the clue that could unravel it all. Our first method for measuring the cosmic expansion is like being a cosmic archaeologist. We look back in time, all the way back to the universe's baby picture. This is the cosmic microwave background, or CMB. It is the faint leftover glow from the Big Bang, a relic light that has been traveling across the cosmos for over 13.8 billion years. This ancient light isn't uniform, it's mottled with tiny temperature variations. These subtle hot and cold spots are the seeds from which all future structures, including our own Milky Way galaxy, would eventually grow. They are a fossil record of the early universe, containing all the information about its initial ingredients and the physical laws that governed it. By studying the patterns in this CMB, cosmologists can build a model of the universe. Think of it as a recipe. The CMB tells us the exact amounts of dark matter, dark energy, and normal matter that were present in the early cosmos. Using this recipe, and our best understanding of physics, the standard model of cosmology, we can run the clock forward. We can predict how a universe with those starting conditions should have evolved and expanded over the past 13.8 billion years. This calculation gives us a prediction for what the expansion rate ought to be today. It's a beautiful piece of theoretical and observational science, connecting the dawn of time to the present day. The result from this method is remarkably precise. The Planck satellite, which mapped the CMB with unprecedented detail, tells us that the universe should be expanding at a rate of about 67 kilometers per second for every megaparsec of distance. A megaparsec is just a very large unit of cosmic distance, about 3.26 million light-years. So, for every 3.26 million light-years further away you look, a galaxy should be receding from us 67 kilometers per second faster. This number is derived from the physics of the primordial universe, a prediction based on the cosmos in its infancy. It's a cornerstone of our standard cosmological model, a figure we thought we could take to the bank. But science demands verification. You can't just rely on one method no matter how good it is. So we have a second completely independent way to measure the expansion. This method is more direct, like using a cosmic radar gun on our local cosmic neighborhood. Here, astronomers look at relatively nearby galaxies. They measure their distances using special stars called Cepheid variables, and a type of exploding star known as a Type Ia supernova. These are our standard candles because their intrinsic brightness is known. By comparing how bright they appear to how bright they truly are, we can calculate their distance with astonishing accuracy. We then measure how fast they are moving away from us by observing their redshift. When astronomers use these standard candles, the Cepheids and supernovae, to build what we call a cosmic distance ladder, they are directly measuring the expansion of the universe as it is happening right now, in our own cosmic backyard. It's a painstaking process of measuring distances step by step, from our nearest neighbors out to more distant galaxies. This approach doesn't rely on the ancient light of the CMB or assumptions about the early universe. It is a direct observation of the modern cosmos in action. It is a completely different ruler, measuring the same thing, the Hubble Constant. And this is where the trouble begins, where the cosmic mystery truly deepens. The number this second method gives us is not 67, it's 73. Using the Hubble Space Telescope and other powerful observatories, teams of astronomers have refined this measurement over years. They have measured dozens of supernovae and Cepheids, reducing their uncertainties to a bare minimum. The result is consistently, stubbornly, around 73 kilometers per second per megaparsec. The teams behind this measurement are confident in their data. The teams measuring the CMB are equally confident in theirs. Both are the work of world-class scientists using state-of-the-art instruments. Neither side can find a flaw in their own work, or in the work of the other. We are left with two numbers that cannot both be right. This isn't just a minor statistical fluke. The gap between 67 and 73 is now so significant that the chance of it being a random error is less than 1 in a million. Scientists call this a 5 sigma tension, which is the gold standard for a discovery in particle physics. It means this is real. The universe is telling us something, and we are struggling to understand the language. This discrepancy, now famously known as the Hubble Tension, represents a potential crisis in cosmology. It suggests that our standard model of cosmology, the grand narrative of the universe that we have built over the last half-century, is either wrong or, at the very least, incomplete. Why does this matter so much? Because the Hubble constant is woven into the fabric of almost every other cosmic calculation we make. If we don't know how fast the universe is expanding, we can't be certain of its age. A faster expansion implies a younger universe. It also affects our calculations of the universe's size and its ultimate fate. Will it expand forever, or will it one day collapse back on itself? The answer depends critically on this number. The Hubble tension is like finding a fundamental flaw in the foundations of a skyscraper. The building is still standing, but we have no idea why, and we are suddenly very worried about its future. Faced with such a perplexing problem, scientists do what they do best. They propose new ideas, sometimes even wild ones. One of the more intriguing, though controversial explanations for the Hubble tension is the cosmic void theory. This idea suggests that we might be living in a peculiar part of the universe. Perhaps our galaxy, the Milky Way, and our nearest galactic neighbors are situated inside a vast, ancient bubble that is emptier than the cosmic average. Now, this isn't a true vacuum, just a region of space, with a significantly lower density of galaxies, matter, and dark matter than elsewhere. It would be an enormous underdensity, stretching for hundreds of millions of light-years across. How would this cosmic bubble explain the Hubble tension? Imagine you are in a slightly less dense part of a swimming pool. The water pressure around you would be lower, and the surrounding denser water would push outwards, creating an outflow. Similarly, if we are inside a giant cosmic void, the greater gravitational pull from the denser regions of the universe surrounding the void would pull galaxies away from the center. This would create an extra local push or outflow. For astronomers measuring the expansion rate locally using supernovae, this local outflow would add to the overall cosmic expansion, making it appear faster than it really is. It would inflate the measurement, pushing it up towards that troublesome 73. This explanation is clever because it allows both measurements to be correct in their own way. The CMB measurement of 67 would represent the true, global average expansion rate, of the entire universe. It's the big picture view, unaffected by local peculiarities. Our supernova measurement of 73, on the other hand, would be a perfectly accurate measurement of our local expansion rate, but it would be biased by our unusual position in the cosmos. We would simply be measuring a local speed bump in the cosmic expansion, not the true speed of the universal motorway. It's an elegant way to resolve the paradox without having to tear up the laws of physics. However, this cosmic void theory has some serious problems. For one, a void large enough and empty enough to create the observed discrepancy would have to be enormous and exceptionally barren. Statistically, the chances of our galaxy randomly ending up in such a special and unusual place in the universe are incredibly small. It would violate the Copernican principle, the idea that we do not occupy a privileged or special position in the cosmos. Furthermore, when we map the distribution of galaxies around us, we don't see compelling evidence for such a gigantic, simple void. While the universe is lumpy, we don't seem to be at the center of a bubble quite this extreme. If we are not living in a cosmic void, and both measurements are correct, then we are forced to confront a far more revolutionary possibility. Perhaps the problem isn't with our location, or our measurements. Perhaps the problem lies with our understanding of the universe itself. The Hubble Tension could be the first major crack in the standard model of cosmology. It might be the first observational evidence telling us that our fundamental theories of physics are incomplete. This is a thrilling and simultaneously unsettling thought. It suggests that there are new forces, new particles, or new rules governing the cosmos that we have yet to discover. What could this new physics look like? One possibility involves the period just after the Big Bang. Perhaps there was an extra burst of early dark energy that briefly accelerated the universe's expansion in its youth before fading away. This would change the conditions of the early cosmos, altering the calculations from the CMB and bringing its prediction for the Hubble Constant into alignment with the supernova measurements. Another idea is that dark matter isn't as simple as we thought. Maybe it has some form of interaction with normal matter or radiation that we haven't accounted for, which would subtly change the expansion history of the universe. Or perhaps the mystery lies with dark energy, the enigmatic force that is already accelerating the expansion of the modern universe. Our current model assumes that dark energy is a cosmological constant, meaning its strength is unchanging over time. But what if it's not constant? What if its power has been growing over cosmic history? This phantom dark energy would cause the expansion to speed up more than we expect, which could explain why the local measurement is higher than the one predicted from the early universe. Each of these possibilities would require us to add a new, unknown ingredient to our cosmic recipe, to rewrite a chapter of fundamental physics. For now, the Hubble tension remains the biggest mystery in the universe. It is a puzzle that has mobilized astronomers and physicists around the world. New telescopes, both on the ground and in space, are being designed with the express purpose of attacking this problem. They will measure the CMB with greater precision and build cosmic distance ladders that reach even further into the cosmos. Finding the answer won't be easy, but whatever it turns out to be, a cosmic void, a new form of energy, or something nobody has even thought of yet, it will be profound. This isn't a crisis to be feared. It's an opportunity. It is the beginning of a new chapter in science, a clue that could lead us to a deeper and more wondrous understanding of the cosmos.